Alrighty, now this is gonna be, let me just go ahead. This 102, chapter 22, which is gonna be electromagnetic induction. Let me go ahead. Get this in. So electromagnetic induction, actually, let me just go ahead. We start by, let's say I have a box. So I got this big old box right over here. It works. All right, so let's say you have in this box, and let's say in this box you have air. So you got air particles. So let's say in the bottom, your air is more denser, and on the top is less dense. So let me start off by defining what a flux is. So flux is how much of something is floating through a surface in a given amount of time. As we mentioned, let's say we got these particles of air inside this little box, and the air is actually moving in a velocity. So let's just go, you got the air particles going this way. And let's say I put a net. So let me actually get a blue on this one. So if I put a net right over here, so we put a net over here where the air particles are going. And if we think in terms of flux, is how much air is actually traveling through that net in that certain amount of time. Let me actually write this down. How much air is traveling through the net in a certain So let's say you have put a net over there and you catch those air particles. Now let's say that means you have same density, large flux. So you got, let me actually just take a more blue on this one. So this one will be same density. Which is going to be a large amount of flux move, which is how much air moves through the surface. Now let's say I take this net and let's say I put it right over here. Actually, let me take a different color in this net. So let's say I get a net and just put it over here, and then I increase the area of that net going in, and just get some more air particles over here that's more dense than the ones down here. So what would happen if I actually take that net and increase the area of it? Well, there's going to be more area, which means you get more flux. Now, if you take the, let's say the blue net, our first net that we got over here, and you put it right over here, would you have the same flux? The answer is no. This is actually going to be smaller density, like we said, which results in a smaller flux. We call it less air particles. So let's say I'm just going to go, let me actually get green of this one. Let me just put this over here more. Sorry. From more to less going over there. And that's what we're talking about, is how much of something is flowing through a surface in a given amount of time. If you put that net where you got your air molecules going in, right? The more air molecules going in through that net, the more flux you have. If you actually increase the area of that net that we have, you're gonna catch more air particles. If you actually take that air particles somewhere less dense, which means that net has less air particles to deal with, that means you're gonna have a smaller flux. So basically what we're talking about in this example is how much air is traveling in a given amount of time. Now let's look at it from a magnet, from magnetic. So let's say you have a magnet. So this is our magnet right over here. This is our north pole, this is our south pole. And you got the magnetic field going in from north to south. Actually, let me just go ahead and write down on this flux. Now, this is what we're going to be talking about is your magnetic flux. Now, looking at the magnet when you have magnetic fields, same thing. Let's say you get our little, let me get a different color for that, little net and put it across right over here. So what we're gonna do, we're gonna end up catching those magnetic fields, which is that's what we call your magnetic flux. Now, one thing we forgot to mention, let's say, let me get a different color, let me get orange. So let's say we get our net and we decrease the area. Let's say we have it sideways, where all the air particles are going on top of it and the bottom of it. In this case, we would actually have zero flux. Same thing, let's say if we have the net, our little net going in sideways, it'll be zero flux also. Now coming back to our example, let's say we take our net, we take our coil of wire, our net, which is going to be our coil of wire, and we actually put it in. Let me actually try to get it in a different color. Let's say we put it in sideways towards sleeping. So this is going to be zero magnetic flux. Well, let's say if you take this and you take it out, let's say we put it right over here. Well, same thing, you're gonna get zero magnetic flux because nothing is flowing through it. Now, your magnetic flux is gonna equal to your magnetic field multiplied by the area cosine theta. Now, your current flowing through a wire can induce it. Now, this current flow going through the wire can induce a current. So let me actually go write this down. Now, your current flowing through a wire can induce a current in a loop of wire. And that's what we're doing. So if we put a loop of wire, you will induce a current. Now we put a large surface right over here. Of course, where you're going to have a large flux, which generates current. So current flowing through a wire can induce a current in a loop of wire. That means if you have a current, you can induce a magnetic field. And same thing, let's say if you have a change in your magnetic flux through the loop, that's also can induce a current. So let's say, I don't know, let me go ahead. Let's say these are magnetic fields and they're coming out towards the screen. So they're going towards you. So these are the arrows. Let's say this is the arrows going in towards you. So let me just write this down. So this is your, actually this over here, magnetic fields going toward you. And let's say I put a loop of wire in there. Let me get green and just put a loop of wire. And I'm going to say the loop of wire is going to be right over here. Now, through that loop of wire, you're going to have a current going in. So that current will be going in through the loop of wire that is created by the magnetic flux. That's your current. And this is along, let me actually put the current in a different color. So this is your loop of wire, and you got a current. Let's say the current is in blue, so you got your current going in. So that's your current. Now, if you actually take this loop of wire and you moved it towards the center of the magnetic field, you will have more magnetic flux. Let's say you take this loop of wire, I'm going to get a different color, you just put it right over here, so you will have a more magnetic flux. If you actually take this loop of wire to the opposite side where there's going to be less magnetic flux. So the change in magnetic flux will create a voltage that causes the current to flow. And that's what we're actually talking about Faraday's law. Make sure we get a different color. So Faraday's law, which states that the voltage that's grounded the generated, let me just go voltage generated, G, and is going to equal to minus N change of magnetic flux divided by the change of time. Now your N, that's going to be your number of the loop. Number of loops of wire. Now the negative sign is actually get a different color. It's a reminder, it's actually put in over there because for us to reminder to use Lenz's law. That's why that's negative, is over there. Now, what is Lenz's law? Now, before I go with Lenz's law, let me just mention one more thing, that, let me go ahead and get orange, that this voltage generated is actually an electromotive force. Electromotive force, which we give your EMF, which sometimes you go as your energy, which is your average electromotive force induced voltage. Which we're going to get back to that in just a second. So the voltage generated is minus N, the change N. The change in the flux divided by the change of time. Now, and again, the negative is a reminder to use Lenz's law. Now, what is Lenz's law? So we got this. So basically what we have over here, let me actually redraw what we got. So over here, let's say that the loop of wire where your magnetic field is going towards you. So let's say this is the loop of wire over here. Just right, do this one over here and do this one right down over here. And let's say this is the magnetic field. We actually were looking at it this way. We were looking at it that way. So let's say this is the magnetic field going in. Now, which way is the current is going? So you got a magnetic field. And let me just go ahead and label this. This is your wire. And you got an increased flux. Now the question is, the current going clockwise or counterclockwise? Now, well, according to the right-hand rule, let's say if you go over here, what you're gonna have? Let's say, I'm gonna just go ahead and try to draw a finger. So let's say this is your right hand coming in. And here's your 1, 2, 3. That's your finger. And these are your fingers wrapped up. Let's say this is your hand rule. So according to the right hand rule, let's say if you have, well, before we start that, I forgot to mention, we only have two choices as either the current is going that way, counterclockwise, or it's going clockwise. So which one was it? So let's say we apply the right hand rule. I try to draw a hand over here with the fingers. And we said that the current going over there, that means flopping in, that's gonna be your magnetic flux, which means that you're gonna have a flux generated going in the same direction. Well, if that happens, what would happen, right? If that happens, that means you would actually have more flux, more current, more energy, which violate the laws of energy. So this scenario over here is completely wrong. Looking at the other one, let's say we have a right-hand rule, and let's say we draw it. So let me actually go ahead and draw this one. So this will be. So this is your fingers going in the opposite. That means your flux is actually going in with your fingers going in opposite direction, which means you would only have the current. You would not have more current and more magnetic flux. So let me go right ahead. In this scenario, the more current, the more magnetic flux is going to be generated, which means you're going to have more current, which means you're going to have more energy going out of nowhere. Which violates the law of energy. Energy can be created and destroyed. So you cannot create more energy. So in this case, your flux, your current is going to go on this side according to the right hand rule. So the current going to induce a magnetic field, and that's what Lenz's law is. Let me actually go ahead and get a different color. Let's write down Lenz's law. The current will induce a magnetic field that counteract the change in flux. And this is your Lenz law. So let's do an example, shall we? Let's say if I have, let's say this is your loop of wire. Let me draw it better than that. Let's say this is your loop of wire and this is your loop of wire after. And let's say in this loop of wire you have a resistor of 2 ohms. And let's say you have a magnetic flux generated. Let me get a different color. Because I already used red. Let me use purple. So let's say you got a magnetic flux generated at 5 teslas, and after the loop, you end up getting 10 teslas. And let's say this was, I don't know, 2 meters by 2 meters. And it took, let's say your time lapse was 4 seconds. So again, according to Lenz's law, this is going on top. That means we need the flux go on the other side. That means we actually have the current going in this way. We actually go in according to our right hand rule that we just drew. Now, when you go from the first picture to the second picture, that's where you're gonna have your change in magnetic and your flux. So, your change in flux initial is gonna equal to your magnetic field multiplied by your area. Now, your area in this case is gonna be what? Your 2 times 2, which is gonna be 4 meters squared. And our magnetic flux initial is 5 Tesla. So that would make our initial flux at 5 times 4, which is going to be 20 Tesla meter squared. Our final flux right over here is going to be equal to Tesla. It's going to be equal to 10. So BBA, which is going to be your 10, multiplied again by 4. So it'll be your 40 T Tesla meter squared. That means your change in the magnetic flux is going to equal to your change in your final minus your change in your initial, which is going to equal to your 40 minus 20, which is going to equal to 20 Tesla meter squared. Now your voltage generated from Freddie's law, you get minus N change of flux over change of T. Now, let's say we have one loop, that means N is gonna equal to one loop, so that means your generated voltage is gonna equal to minus, and I'm just gonna keep the minus over here just to remind us to use Lenz's law, and that's what we just did earlier. So it'd be, the change of flux would be 20 divided by the time, the change of time, which is gonna be 4 seconds, which is gonna equal to minus 5 volts. Now, let's say you want to find out what is, let me go ahead and write down, now, let me get a different color. Let's say you want to find out what is the current. That means your current, your voltage is going to equal to IR. That means your current is going to equal to your voltage divided by your resistor, which is going to equal to your 5 divided by 2, which is going to be your 2.5 amps. Now, let's take another question. Let's take another example. Now, supposedly, or another situation. Now, supposedly we have our little loop of wire, and you got your magnetic fields coming up. And let's say you got a cylinder with length L down there that you roll at will to some kind of length. So let's just go ahead. This is cylinder with length L. Now, when you roll the cylinder, that means you're gonna have a new area. Now, your electromagnetic force that we talked about, which is your generated voltage, again, is minus M, change of flux over the change of T, which is, let's say we have one loop, so it'd be minus 1 multiplied by delta flux divided by change of T. Now, the change of flux, that's going to equal to what? It's going to equal, so that's negative. Just go ahead. Your magnetic field multiplied by your area, your change of magnetic field divided by the area divided by your change of time. Now, your area is going to equal to what? Now, the area is going to equal to, let me actually go ahead and write this down in different color. The area is going to be equal to your length times your length. In this case, this is your first length right now over here. So this is going to be your length multiplied by this length over here, which is going to be the distance. Let me actually go right down. Go ahead, distance. Now, what does your distance equal to? Remember we said that velocity equals your distance over time. That means your distance is going to equal to your velocity multiplied by your change of time. So this distance over here, let me go ahead and write this down, is going to equal to, let me actually, this length over here. So this is going to equal to V delta T multiplied by that length. So what we would end up having for your electromagnetic force, we would have your magnetic field multiplied by your velocity multiplied by, make sure I write this down, your velocity. Multiplied by that length divided by delta T. Again, your delta T is going to cancel out. So what you would have is your electromagnetic force is going to equal to your VBL. Your velocity multiplied by the magnetic field multiplied by your lengths for that rod. Now, the force that is actually pushing, and when you're actually pushing this, you're going to have a force. Let's say you do it by hand. Let's say, I don't know, let's say this is by hand. Which creating a velocity this way, and this is going to be opposite force going opposite. So your force is going to equal to your current multiplied by the length multiplied by your magnetic field. And this is what we talked about. So we looked at electromagnetic induction, and each charge within the conductor is moving and experiencing magnetic force, which is going to be QVB. We actually need to write that down. So your force is also going to equal to QVB, your charge multiplied by the force, or multiplied by the velocity, multiplied by your magnetic field. So let's do an example over here, shall we? So supposedly a rod is moving with a speed of 5 meters per second perpendicular to 0.8 Tesla's magnetic field. The rod has a length of 1.6 meters and negligible electric resistance. The rails also have a negligible electric resistance, and the light bulb has a resistance of 96 ohms. Find the electromagnetic force produced by the rod and the current induced by the circuit. So in order for us to find the magnetic force, we get speed is 5 meters per second with a 0.8 Tesla with a 1.6 meters. So let me go ahead, and this was example 1 in our notes. We said that the velocity was 5 meters per second, and your magnetic field is 0.8 Teslas, and the length was 1.6 meters. And for part A, we want to find the EMF, the electromagnetic force that we want to find, which we said is going to equal to your VBL, which is your velocity, which is your 5 meters per second multiplied by your 0.8 Teslas multiplied by your length, which is going to be 1.6 meters. And plugging that in, we should get 6.4 volts. Now, for part B, we want to find the current induced. So your current is, again, we saw it's your V over R, which is your generated voltage. So this is going to be 6.4 divided by Now your resistance is going to be 96 ohms. Let me go ahead. 6 ohms, so this is going to be 96. 6.4 divided by 96, it will be 0.067 amps. And, yep, and that's exactly what we got. And that should conclude chapter 22 for Physics 102. If you have any questions, go ahead and email me at abunaem@uah.edu, or you can give me a call at 256-348-1480. You can text. Thank you so much.